Hello, everyone, and welcome to the Thursday session of the press conference at the 49th DPS. My name is Shantanu Naidu. I'm the DPS press officer, and with us is also Rick Feinberg, who's the AAS press officer. We have 4 very interesting talks today. On my right is Chrysa Avdellidou, who will be presenting from the European Space Agency, who will be presenting tracing the near-Earth object size distribution with lunar impact flashes. To her right is Gina DiBraccio from NASA Goddard Space Flight Center, who will be presenting the complex magnetic field of the Martian Magnetotail observed by Maven. To her right is Casey Lisse from Johns Hopkins University, who will be presenting narrow circumstellar debris rings in young systems, evidence for planetary formation from multiple subcores. And to his right is Alan Stern from Southwest Research Institute, who will be presenting an answer to Fermi's paradox in the prevalence of ocean worlds. So we'll first start with the 4 presentations, and then we'll head to Q&A. Before we start, could you please silence your cell phones? And I'll hand it over to Chrysa. Thank you.
Okay, thank you very much for the invitation. It's a great honor for me. It's my first DPS, and I'm very glad that I give this talk today. I will present the work that I did past summer, and this is an ESA-funded project. It started earlier this year, and I'm going to present the first results and also the implications that we're going to have from this study. So, okay. What is an impact and how we observe it? This is this is, if you can see, now you can see an impact that lasts 4 frames at the surface of the moon. This was obtained on the 1st of March earlier this year. So I'm going to talk about these events. So the official motivation in order to do this project is to understand, to measure the size-frequency distribution of the very small near-Earth objects. This is very important, mostly for the space assets. And let me demonstrate something. This is panels of the Hubble telescope that I had in my previous university, the University of Kent, and you can see impacts of micrometeorites. So we try to trace the size distribution in a little bigger scales than these centimeters and decimeter scales. So why we observe the moon? Because the moon offers a large area in order to do the surface. Also, we do not have the atmosphere there in order to slow down the impactors. So whatever we get, we can study it in a more accurate way. So the idea was introduced in 1993 by Melos, and we have now almost 20 years of observations of lunar impact flashes. So let me tell you a very short story. About 900 years ago, there were some monks in the UK that they claimed that they saw a huge impact on the moon. Actually, the moon broke. So for many, many years, it was people were trying to find where is this crater on the moon, because such a big event should create a large crater. So they thought that this crater could be Giordano Bruno. Okay, Giordano Bruno is young, as we saw earlier today, but for sure not 900 years old. So then we said, okay, what could be this event? So the most possible explanation is that it was a meteor, it was a bolide that hit the Earth atmosphere, the line of sight coming from the direction from the moon, of the moon. Still, it is a mystery, we're not very sure. So a few words about the project. So the project happens in Greece, as you can see in this map, in the mountain, in Peloponnese area. It is called Neliota, that stands for near-Earth object, lunar impacts, and other optical transients. This is ESA-funded project. So the telescope was refurbished. It belongs to the Observatory of Athens, and the operations will last at the beginning for 22 months. We are already during the first year of observations. So the telescope is 1.2 meters in diameter, but the novelty for this instrumentation is that we observe with actually 2 eyes in reality. so one in R and one in infrared simultaneously. We can have fast acquisition, about 30 frames per second, and this is important because the duration of the flashes, as you can see, is very, very, very short. So we want to have good time resolution when we cast the long events. So far, we have 22 validated events. This gives us a good rate so far compared to the other surveys that happened from Spanish teams and from NASA teams. We have so we have one flash every 1.8 hours. And here I have to say that the duration, we measure it at the infrared mostly, the camera, because as I will show you in the next slides, we are talking about, okay, the temperature rises for our standards, but still they are very cool events. So here, a very good friend of mine, Steven Schwartz from University of Arizona, he gave me this simulation for this presentation just to demonstrate how an impact is working. So what we try to do in order, as a final product, to have the size frequency distribution is to measure the temperature that have the droplets that decompose the plume of the impact, the ejecta. So first of all, we have to do a big assumption that the flash that we see on the moon behaves as a black body. This is a big assumption because currently we are not 100% sure that this is a mechanism, not only us, but generally people who are working on this field. So this is something that we can also investigate better. So the important, from the color of the flash, we can have for the first time estimation of temperatures of flashes. So actually we use the lunar surface as a big scale hypervelocity laboratory. And because we have very fast acquisitions, as I said before, we can see actually the evolution. So how the plume, the ejecta, cools down after the impact. So, okay, let me continue. This is a plot that I managed to finish a couple of days ago. This is with all impacts that we have detected, validated impacts that we have detected so far. Validated impact is the one that has been detected in both cameras, so in both wavelengths. That's why we can derive also the temperature. So as a further step and great implication is we try to understand which every impact with mass which is a mass that can give us from the impactor in combination, which is temperature, and also in combination with the location that is impact on the moon. So I would like to show you how we do this. We started actually this work in the University of Kent, where there is a two-stage light gas cannon. We try to simulate the flashes that we see on the moon, but inside the lab. So we have lunar simulant, we have basaltic projectiles, so we fire them in the lab, and as you can see, so the video will play again and again, you can see that also the color of the flash depends on the material that it is impacted the surface. Our temperatures so far are in a good theoretical agreement. So they range between, they start actually from the melting point of the lunar regolith. So we are very glad for that we are in agreement with theoretical studies. However, we have still small statistics, so we'll see we have surprises in the future. You can learn something more. The masses that we can now derive are between some grams and kilograms. However, there is a big difficulty is that since so far we detect sporadic events, so impactors that they don't belong to a meteor stream, we cannot have a good estimation of the velocity with which they impact the lunar surface. But on this, it depends the luminous efficiency. Luminous efficiency is actually the fraction of the kinetic energy that goes to the luminosity of the event. That said, that the size frequency distribution, the estimation of the sizes is a bit tricky because first we need to have a broad, at least, understanding of the origin of the impactor, or if you can have a hint of the density, as I showed before with the plot on the lunar surface. So future work, as I said before, we start at the University of Kent in order to couple both observations and impact experiments in the lab. We try to determine all these different parameters as speed, mass, cratering, the volume of the crater that we create, the ejecta, the velocity of the ejecta, the light, and the temperature that we get from the flashes, plus the duration of the flashes. So we want to debias, first of all, compositionally the impacting population in order to have better estimation of the sizes. And the other important thing is that for the impact physics itself is that we want to see how much of a black body is a flash, what actually are the components, what are of this light, and what are all the processes that accumulate in order to produce this light. This also will help in the energy partitioning, so how much energy after the impact goes to the ejecta in order to fly away from the target, the debris, how much will go in order to produce the light, how much to excavate the crater, and so on. So thank you very much.
Okay, we'll pull my presentation up. And while it's loading, I'll just introduce myself. So my name is Gina DiBraccio, and I am the Maven project scientist. So thanks for having me here today, and thanks for joining me. I'm going to be talking to you about the complex magnetic field of the Martian Magnetotail as observed by Maven. So Maven observations have changed our understanding of the structure of the Martian magnetosphere. We're finding that a majority of the magnetic fields in the Martian magnetosphere are open to space. And this is really important because these open magnetic fields are actually creating a pathway that atmospheric particles can escape to space. So today I'm going to be talking to you about how these open magnetic fields are formed and how we're observing them with Maven. So through a process called magnetic reconnection, magnetic fields are able to come together and combine to form a new type of field line in the Martian environment. And during magnetic reconnection, local particles are also accelerated as well. So using a combination of Maven observations and simulations, we're able to confirm this new structure of the Martian magnetosphere. So if you take a look at the figure on the left, I'm showing a cartoon of our prior understanding of the Martian magnetosphere. So what we used to think was that a majority of the magnetosphere was formed as the sun's magnetic field came and draped over the Mars planet itself, directly interacting with the atmosphere. So as these yellow magnetic field lines, as I have them drawn here, come and drape around the planet, it forms this induced magnetosphere. But then what you see on the right is our new understanding, what we're finding, where we still have these draped magnetic fields of the sun that are colored in yellow, but we also have the blue crustal fields of Mars that are shown in blue. They have each end attached to the planet. And then we also have these newly opened magnetic fields that are red. So they have one end attached to the planet and the other streaming behind, open to space. And so what we're finding is there are these three different types of magnetic fields at Mars. So we have the draped fields, the closed fields, and the open fields. And just to clarify, we can't actually see magnetic fields with our eyes, so these colors are just to show you the different types that we're working with here. So as I mentioned, the magnetosphere is formed as the sun-solar wind directly interacts with the upper atmosphere of Mars. So this movie does a nice job of showing the solar wind, which is a high-speed gas filled with charged particles, directly interacting with the planet and forming this magnetosphere. So unlike Earth, Mars does not have a global magnetic field, but there are these crustal fields. So crustal fields are pockets of magnetic fields that are spread across the surface of Mars, and they're free to rotate with the planet. So as they rotate with the planet, they're constantly changing the obstacle that the solar wind is facing with Mars. So if you watch the video, as the solar wind particles stream around the planet, the area behind the planet becomes elongated, and that's the magnetotail. So that's the area that we're focusing on with our data and simulations for the remainder of this. So as I mentioned, magnetic reconnection changes magnetic field structure, and it also accelerates particles that are nearby. So with Maven, we're able to directly observe magnetic field observations, and we can also observe these three different types of magnetic fields that I was talking to you about. So we can observe the open, the closed, and the draped fields. So through these cartoons, we're demonstrating how reconnection occurs at Mars. So once again, if you look at the before panel, we have the yellow magnetic fields that are the draped fields coming from the sun, and they're going to come right up to the planet and directly interact with the blue magnetic fields, which are the closed crustal fields of Mars. So as the yellow and the blue magnetic fields come together, they form these new open fields that are drawn in red in the middle panel, and those red fields are the open magnetic field lines, so they have one end attached to the Mars surface, and then they're opening up to space, free to let those atmospheric particles travel along the field lines. So yellow and blue continue to come together, the draped and the closed fields, to make these newly open fields. In the after picture, we have many of these open fields that are forming in the Martian magnetosphere. So what we're finding with Maven is that a majority of these magnetic fields in the Magnetotail are open to space. So they have this open magnetic field topology. So using Maven data and modeling results, not only have we identified these open fields, but we're revealing that there is actually a twist in the Martian Magnetotail that's directly indicative of these effects of magnetic reconnection. So in the figures that I'm showing you here, on the left are the Maven data, and on the right are our simulation results. So in both of these figures, the view is as if you're standing at the sun, looking towards the planet down into the Magnetotail, and everything that's red are magnetic fields that are pointed out of the page towards you, and blue is into the page away from you. So you'll notice that when comparing the data and the simulation results, the red and the blue areas compare very nicely with each other. But you'll notice that they're also twisted, so they have this asymmetric shift to them that was really interesting for us while we were examining these data and simulation results. And so what we found was that this twist was a direct result from magnetic reconnection occurring. So we went one step further to confirm this by running our simulations a little bit more. So we ran our simulations without reconnection and with magnetic reconnection. And so you can see the difference here. So when there's no magnetic reconnection occurring between the draped fields and the crustal fields, we have this nice symmetric distribution between the red and the blue areas, but when there is reconnection, you can see how this twist starts to occur in the Martian Magnetotail, and that's exactly what we're seeing with the Maven data. So to summarize here, we're finding that a majority of the magnetic fields in the Martian Magnetotail have this open topology. And as I've said, these open fields are created by a process called magnetic reconnection. And reconnection changes the magnetic field structure, but it also accelerates particles that are local in the atmosphere of Mars. And so using these data and modeling results, we revealed that there's this twist in the Martian Magnetotail that's directly indicative of the results of magnetic reconnection. And these results have changed our understanding of the Martian magnetosphere. So we're continuing to learn more about it, and it's really exciting, especially because these results have implications for atmospheric loss to space. So finally, the main takeaway points from this presentation is that with Maven, we're seeing previously unobserved magnetic field variations due to magnetic reconnection in the Martian Magnetotail. So as I mentioned, reconnection accelerates particles, and it may actually drive much of the atmospheric escape to space at Mars that we're observing with Maven. Thank you.
So good afternoon. While we're setting up, I'm going to give a presentation today that shows you what I do when I'm not flying through our Kuiper belt with Alan. I look at other people's Kuiper belts. Okay, I see it here. No signal. It's not good. I have it on my screen. Jazz Plankton. It's resetting. Looks like it's trying to find it. Ah, there we go. Very good. Thank you very much. So I hope it stays. Thank you very much. So today I'm going to talk about three very famous young debris disk systems. 4796A, Fomalhaut, and HT32297. I apologize, for me, they're obvious numbers. For you, it's probably HR and HT telephone number, but hopefully by the end of the talk, you'll get them. These are systems that have been looked at for decades. What we are doing is actually, rather than making pretty pictures like you see there in broadband photometry, which tells you the morphology and the structure, is we're going after what are they actually made of. And what does that imply about how they get there and where they're going? So these are 3 A-star systems. These are very bright, hot stars compared to the sun. They're all young, so they're 10 to 300 million years old. The stars themselves are all about 20 solar luminosities. They're very bright. The masses of these rings, if we go integrate from the tiniest dust all the way up to Kuiper Belt objects, they're on the order of Earth masses. So there's lots of mass there. There's planet-forming masses there. And the temperature of the rings is what's important. The temperature for the ring that we studied in depth is 100 Kelvin. I'm going to come back to that later. The other 2 are much colder, and that's got strong implications for what's going on in these rings. So let me go to the next slide. The work we've done is all based on a survey, which I'm very proud to call NERDS. It's the Near Infrared Debris Disk Survey. And it was, basically, we've looked now at more than 60 systems, 100 plus hours. It was done at the IRTF, NASA IRTF on top of Mauna Kea. They've been very generous as giving us time over since 2010. And it can do fantastic work. It's 1% precision near-infrared spectroscopy from 1 to 5 microns. If you look in the lower right, you can see that's a detail of the kind of data we get. I'm going to give you a much broader grasp, but we can get all kinds of interesting gas lines if they're there. So, they say never show spectra in a talk. I'm going to, and I'm going to walk you through it quickly, because the important thing here is you see these are a whole bunch. This is 7 different A-star spectra. Our exciting guy is on the top in blue. And you'll notice the difference between him and the other 6 is that the black is the model. That's what the black is the data. The blue or the gold is what we know and expect from the star. You'll notice that the black slowly but surely exceeds the model, what's coming from the star, from 2 to 3 to 4 or 5 microns for HR 4796A. That means there is stuff around the star that is glowing and giving off near-infrared radiation. The other stars, we consistently just don't see anything. There's one exception, 13148. That's just a normal giant asteroidal debris disk. It's another kind of thing, which I'll talk about hopefully another time. When we take that excess and we figure out, we divide by the star's light, because it has to be scattered light. It's way too hot to be a thermal emission from dust. We see this curve. This is basically what we call, in the planetary business call IRF, or another way of putting it, this is the reflectivity of that dust. You're seeing this ring, and this is the spectrum of its reflectivity. If we compare that to known reflectivities of things in our outer solar system, the only thing that looks like that stays red from 1 to 5 microns, is the surfaces of evolved, burnt out comet surfaces of nuclei. We don't see it for Centaurs, we don't see it for Pluto, we don't see it for Charon or Quaoar, we don't see it for Trojans. Nothing is that red. So the only thing that's that red are comets, or comet nuclei, and the material that comes off comets and get devolatilized. And that's exactly what we're seeing in that ring. So how else do we know that this ring is full of burnt out cometary devolatilized material? Well, just showed you it was very red. We also know that if we take the phase function for cometary dust, we can actually produce the range of brightnesses we see around the ring as you go from forward scattering to back scattering. We know that the temperature of dust, as I mentioned before, is about 100 Kelvin. 100 Kelvin is where the comet Ison and Siding Springs, as we watch them come into the solar system, that's where they turned on. That's where they became active. Before that, they were inactive, they were stable. 100 Kelvin is where you expect comets not to be stable. So if there were comets in a ring, they're no longer icy, beautiful comets. They're actually rubbles of devolatilized cometary material with lots of organics and rock. And finally, we made a prediction, and ALMA is now going to look at this ring. They do not see any gas coming from these bodies. I mentioned about the temperature. I take the IRTF spectrum, you see there, that's from 1 to 5 microns in this plot, and I add it to archival Spitzer measurements of these systems, and it's these beautiful 0.8 to 35 micron spectra you're seeing here. The ring does also emit in the thermal infrared, and that's what you see the big humps coming over the right. We know this is how we know that the 4796 dust is 100 Kelvin. 32297, as I said, another one that looks like it's got a very narrow, beautiful ring, its dust, as we measure when we fit that black body, is only 80 Kelvin. That's where comets are stable. You'll also notice we see absolutely no excess in the infrared. It does not have red dust. So, by contrast, Fomalhaut and 32297 don't show us this red excess. They do have comets, but what they have is comets still full of their ices. So they're still blue, or bluish white. So they look pretty much like starlight, so we don't see much of an excess. This also goes along with the fact that those comets are stable. They're at 70, 80 Kelvin. They're like at Uranus and Neptune kind of comets, which are stable in our own system. And we also went and told the ALMA folks they should see comet gas coming from there because CO does emit out to all the way to Pluto, roughly to Pluto. And indeed, they found CO. So this all makes plenty of sense. Okay, so that's all the backstory. So in a nutshell, what is going on here? 4796 had red dust with no circumstellar gas. So we have thick, localized dust cloud in a very narrow ring made of burnt out comets. It's multi-Earth scale of mass. And it's a very narrow, confined ring, and it's only a 10 million-year-old system. That's kind of hard to believe. 10 million years old, things should be flying every which way. Our system certainly didn't settle down. There was all kinds of inclination, all kinds of collisions. When you're forming a planet, if you come in and you impact and you become part of a planet, you throw off stuff at escape velocity. Escape velocity even for Mars is 5 kilometers per second, which would give you a huge spread compared to the ring we see. So something is making this ring very confined. You notice on the upper right, I've shown you an X. We're not seeing planet formation in that kind of scenario. So the only thing I can imagine, given everything else we've put through, is that we're seeing is a ring that's shepherded by smaller bodies. So I think things may be the size of Pluto or so. And they're forming, and rather than forming a planet in one big lump, you're forming a lot of little lumps, and you're putting it together. This resonated extremely well with Alessandro Morbidelli this summer when I talked to him at the GRC, when he said, oh yeah, we wrote a paper in 2015 arguing that's how you made Uranus and Neptune. So this is really cool. What we think we're seeing is naked outer planet formation. However, we're seeing it when there's no gas left in the system. So whatever is being made, it's going to be big, possibly a super Earth, but it's not going to have any gas clothing around it. So what we think we're seeing is a carbon-rich super Earth being formed. Fomalhaut and HD 32297 still have ices with the comets that are coming together and making a planet. So the only difference, I can go through a whole list, but maybe time is running out. Well, actually, I do have a few minutes. You're seeing blue-gray dust, which is coming together. And it has CO, it has ice, it has water. So and it's still thick and localized. You've still got the same argument for making this narrow, confined ring. So it's coming together. Again, it has to be shepherded. But what you're making there is not going to, it's going to have ices. Again, there's no gas in these systems. They're too old, and we can show that there's no primordial gas. So they're not going to get clothed in the atmospheres you see around Uranus and Neptune. But you're still going to make a giant planet. So instead, the recipe that looks like we're making here is for a gas-poor mini-Neptune. And the reason I poke at the super-Earth and the mini-Neptune is those are the most common abundant planets found in the Kepler survey. So we are hopefully seeing naked planet formation here, very isolated, and that's really cool. And that's the gist of my talk. Thank you.
Or we'll just give it a second to load. All right. Well, one of the most profound questions in the space sciences is whether we're alone. And it's been a question that has been of interest for centuries. And fortunately, we now live in an era where we can actually begin to address this question in a serious way. Let me give you a little background on this. Many years ago, in the early 1960s, about the time of Frank Drake's legendary Project Ozma, Drake and Enrico Fermi and Carl Sagan were at a meeting together discussing the prospects for life in the galaxy and the development of technological civilizations. And Drake had, at that time, just recently parameterized the way that one can estimate the number of technological civilizations in the galaxy with something that's now well known as the Drake equation, which is the product of a series of factors that help you quantify this estimate of the number of possible civilizations. And Fermi ran some numbers, something that many of us have since done, and estimated the number of habitable planets in the galaxy and the probability that each would develop a technological civilization and the length of time that those technological civilizations might last, and came up with a very large number estimate for the number of expected civilizations. And that graphic on the left is indicative of that. And Fermi, being Fermi, a Nobel laureate, asked, well, if I get big numbers every time I run the equation, then where are they? And that is the Fermi paradox. Where are they? And over the decades since Fermi first posed that question, many of my colleagues in the astronomical and planetary science communities have tried to address that issue. And there are many possible explanations for it. One of my favorite papers on this topic is a paper by Michael Hart, published in 1975 in the Quarterly Journal of the Royal Astronomical Society. And although that was very long ago now, already there were dozens of potential explanations. For example, maybe they don't develop technologies, or perhaps they communicate with technologies that we don't yet have, so we can't tell that they're communicating. Or perhaps they don't live very long in a communicating phase. The paper that I gave here at DPS suggests yet another possible explanation for the fact that we don't yet see them, even though there are many predictions that there should be large numbers of technological civilizations. And it comes in the form of an answer that links the prevalence of ocean worlds, water ocean worlds in particular, that we are finding in our solar system to this problem. I'm going to be using the acronym WOW for water ocean worlds in what follows. And you know, at the beginning of the space age, when we looked out only with telescopes and didn't yet have spacecraft to go and examine the far worlds of our solar system, we thought that the Earth was the only world in our solar system with a water ocean. In fact, that turned out to be a selection effect, because although we could look out with our telescopes and find only dry surfaces, icy or barren regolith surfaces across the solar system, in fact, the oceans of our solar system are very different predominantly than the Earth's ocean. They lie on the interior of worlds. And this is a nice illustration of one of those discoveries made at the Saturnian moon Enceladus. But in fact, there are many ocean worlds that are now either suspected or pretty well confirmed in our solar system, and all of them, except the Earth, are interior ocean worlds. And we suspect that there's nothing special about what's going on in our solar system, that interior ocean worlds are probably prevalent throughout the galaxy. Thanks to the Kepler mission, we know that solar systems are prevalent, and we expect, although we have not yet proven, that the same is quite likely for interior ocean worlds. It's really been a revolution in my field that oceans are common across our solar system and very likely across the galaxy and the universe. Now, the thing about exterior ocean worlds like the Earth is you live in a shooting gallery. It's a very dangerous environment to live on the surface of a planet. And we all know about impacts like those that very likely terminated the Cretaceous period and the dinosaurs. But there are many other dangers. You know, you have to have a magnetosphere to protect you from radiation. You're subject to the vagaries of your star. Faint early sun, strong solar flares are all dangers to ecosystems on the surfaces of planets. Poisonous atmosphere is the same. The evolution of your star off onto the red giant branch, which is inevitable for solar-like stars, is another danger. And there are nearby supernovae and giant molecular cloud passages, and the list goes on and on of dangers posed to planets with exterior oceans and exterior ecosystems. But none of these apply strongly to interior ocean worlds. In fact, they're insulated beneath a thick layer or roof of rock and ice, which makes them largely decoupled from all of these external influences. They don't even care very much what orbit they're in. They don't have to be in a habitable zone. An ocean inside of Pluto, very far from the sun, is just as wet and just as warm as an ocean inside of a Galilean moon. So in fact, the interior ocean worlds are much more stable environments and much lower risks to biology. But moreover, they're also naturally insulated from communications. Almost all forms of electromagnetic communication, our radio, if you will, or our optical communications, would not make it out from an interior ocean through that overlying burden of rock and ice. So if some of these worlds develop technological civilizations, the normal things that we look for in the search for extraterrestrial intelligence would not emanate from those worlds, even though they could well have civilizations and technological civilizations in them. Moreover, if the beings in such a hypothetical ocean world were to discover that above that roof there was a surface, and if they were to travel to the surface of their world, it's a real question as to whether they would understand what the lights in the sky are, whether they would develop a branch of astronomy, and whether they would be disposed to space travel as we are. I think there's a fair argument that they might not be. They might, for example, conclude, if they developed astronomy, that all the other worlds that they discovered also, if inhabited, were beneath these deep rock and ice shells like their own, and that might be kind of a Debbie Downer to your motivation for space travel. But in addition, everything we know about space travel with our technology involves making the spacecraft lightweight so that you can accomplish the mission. And if you were from an ocean world, it's quite likely, I think, that you would be disadvantaged by having to bring along all that water that the extraterrestrial dolphins or whales would need. That makes for a very heavy spacecraft, and so they're pretty disadvantaged. So I'm going to conclude that perhaps the universe is teeming with life and even intelligent civilizations that are predominantly in interior water-ocean worlds. Such civilizations would be strongly insulated from communicating with others by the lids above their ocean abodes and would be severely disadvantaged in developing spaceflight as well. So perhaps the answer to Dr. Fermi is that they're all around us. They're simply living inside of the worlds that are near us. Thank you.
Thanks to our speakers for the very interesting talks. We'll take questions now. Please wait for the microphone and announce your name and affiliation before asking question. Kelly.
Always happy to break the ice. Let's see, Gina, you weren't clear, or maybe I missed it, on where these reconnection events occur. From the diagrams, it looked like it was on the day side. Is that right?
Yes.
I think you have to press the button.
Good. Okay, perfect. Yeah, so for the most part, what we think is that they are occurring on the day side of Mars, which makes it even trickier because the crustal fields are constantly rotating. So there's always a different number of crustal fields that are faced on the day side, right? So in the diagrams that we have here, this is essentially with the sun on the left, and the yellow lines would be the magnetic field lines coming from the sun interacting on the day side. We do have magnetic reconnection that occurs on the night side as well, but it likely wouldn't form these open fields. It would actually take these open fields and connect them together to possibly form more closed fields.
And just to follow up quickly, for my edification, these are the these are the remnant bubbles that were discovered.
Exactly.
Okay.
Yeah, so they were discovered during the Mars Global Surveyor era. So we knew that they were there, but with Maven's unique global orbit covering Mars, this is the first time that we're actually able to observe this from a global standpoint.
I have a question. Rich Talcott from Astronomy Magazine. I have a question for Chrysa. You had 22 flashes that you observed, and I noticed some were in Maria and some were in the Highlands. Have you noticed any distinctive signatures or difference between those two? Or are the numbers too small to?
Okay, difference in which sense? On the temperature of the calculation of the temperature of?
Right, the temperature.
Or the rate of the...
Whether you might be able to find some sort of difference between the two compositions.
Exactly, this is exactly what I'm working this period. So we try to understand this, but we need more detailed work. That's why I want to couple also with laboratory experiments by using a lunar simulant, both from Maria and both from Highlands, in order to see how the same impactors react in different. This we can do it in a better way on the moon when we will have a meteor stream. So we have better constrained the impact velocity for all the simultaneous events of the meteor stream, and then we can do probably better statistics than with the sporadic events, that the velocity fluctuates more. Yeah, thank you.
Yeah, Rick.
Yeah, Rick Feinberg, AAS. I'd like to follow up Rich's question. So are you doing concentrated observing during meteor showers, for example? And also, can you remind me how big your telescope is? And if I heard you correctly, you said you were getting, a pretty large number of flashes in a reasonably short period of time. I'm just curious how, how likely is it that, say, an amateur astronomer with a reasonable sized telescope and a CCD camera could be picking these things up?
Very good question. Thank you very much. So first of all, the telescope is 1.2 meters in diameter. So, okay, in order, we have 22 events, that's correct, but these are the validated ones. We have other 10, 15 events that are not validated. Probably they were cold enough in order not to be detected with the R camera. So this is even higher, the rate. The other rate that we can compare that, it is with the rate that NASA gives from their website. Is the work of Rob Sachs, Daniel Moser, and these people, this team, and they give 2.8 hours per event, but they average the meteor streams with the sporadic events. Here, this rate that I present is only for the sporadic events. So when we have also this, currently we didn't have observation of a stream, because when we started observations, we didn't have any good geometry to encounter a stream. The first stream that I think will encounter it will be the Geminids in a few months. So, and we expect to have a higher flux at that period. We were not able to detect also, to observe the Perseids. It was not in a good phase. About the amateurs, so here I have to say that the NASA project has two telescopes that are 14 inches, so they're much smaller than this one. So it depends what is the instrumentation of the amateur astronomers, but also how fast they can get frames. This is another important thing in order to do some better analysis. And the last thing that I want to say, your question was, apart from that, I try to understand the third part of your question to remember. It was
remember myself.
It was first for the. So here, with this project, it is the largest telescope dedicated now for lunar observations. They observe every month when it is favorable, of course, the phase of the moon. Okay, there is not a month or a day that they will skip observations if the moon is detectable. And they hope that the team, that they can detect flashes down to 12th magnitude in the R filter, although so far the NASA project goes until the 10th magnitude. So we hope we will have much more detections at the same time. Thank you.
I'll keep rocking and rolling. So, Dr. Lisse, is Pluto a planet? No.
Yes.
What I wanted to ask you is, if you're using shepherding objects to confine these narrow rings, does that confinement also preclude them from accreting into single objects?
See if I can get this to work. No, actually not. I think you're actually seeing those growing, and then eventually they're going to coalesce, and there will be a planet there in millions of years.
Okay. And for Dr. Stern, if I can just keep going with it. You allude to something that I've always felt was a weak link in the Drake equation, which is the factor that talks about how many civilizations become technological civilizations. And I wonder if you could address that. The analogy I've always used with students is, imagine like in that Kevin Costner movie, Waterworld, Earth, everything evolved the same way on Earth, but we don't have any land. Then the highest forms of life are, the mammals in the oceans, and they're never going to become technologically advanced.
Wasn't that movie a flop?
It was. I hope that your theory is not the same.
Thank you. Well, so I think the question that you're really posing has to do with whether technologies could develop in a WOW or a water ocean world. And, I don't think that we know, other than the example of on Earth, really how frequently or how easy it is for technologies to develop on the surfaces of other worlds. We don't have a second example. And, when we began the space age, our view of the diversity of the worlds in our solar system was pretty pitiful compared to what we found with spaceflight. It's a much more diverse population in our solar system than we expected simply from planetary astronomy. And we've never probed the interior of any ocean world. We have good evidence for several of them and circumstantial evidence for quite a number more, but we don't know how complex those interiors are. And they may well involve islands and potentially pockets of gas and completely habitable environments beyond just the presence of water. They don't have to be fully flooded with water and have no airspace, no place for fire and metallurgy, for example. We really are only at the very beginning of understanding that there are ocean worlds and have no idea what the complexity is. So I would argue, and from a speculative standpoint, that it's only once we've made real explorations of ocean worlds that we'll be able to answer a question like yours. And for now, I would think that it's probably plausibly likely that you could develop technological civilizations inside of these protected water-ocean world environments as frequently and perhaps even more frequently than in the shooting gallery environments on the surfaces of worlds.
Jay.
Alan, to follow up on Kelly's question, Jay Pasikoff, textbook author, here is a textbook author. I seem to recall in a book by, I think, Eddington in the 1930s, the story of astronomers on a cloud-bound planet who developed the laws of physics, and then one day, and they find out about self-gravitating gas spheres, and they work out ranges that they can exist in and how they can evolve, and then one day the clouds are pulled back and they see the stars. So I wonder whether there might be an analogy. I don't see, just as you said, I don't see any objection to evolving the technological situation down below, and then one day one of them pushes up through the ice and is surprised by what is there to be seen. So could that then lead to an urge to explore? If there's an urge to explore, maybe they've developed neutrino astronomy first, but when they push up through the surface, they might learn about some electromagnetic things and try to expand.
Yeah, or perhaps they'll develop very low frequency radio astronomy, which can penetrate very thick overburdens. But to answer your question, Jay, I think it's entirely likely that they might develop an urge to explore, want to go to the top of the roof of their world, perhaps, as we do, go to space and develop the science of astronomy. But I do argue that they would be disadvantaged simply by their need to bring along the warm ocean environment. But with enough trials across the galaxy and across the universe, there might be a lot of that. The question is whether they can develop spaceflight with the impediments that their evolution brings. And I think it's a very rich field, and I hope more people will think about this because it's a new avenue of investigation.
Maybe they're going to Europa because they think it's more favorable for them in their travel, and they don't want to come to something with continents like Earth.
Exactly. Perhaps that's the case.
Do we have
There's something here?
online questions?
Something came in when I wasn't looking. Yes, this is a question from freelancer Rick Lovett out in Oregon. This is for Alan Stern. Let's see. He says, so is what he's doing really adding a new variable to the Drake equation? Basically, he seems to be saying that surface ocean world civilizations are doomed, and we're really lucky to be a very rare survivor.
Well, in the paper that I've written and submitted to the Journal of Astrobiology on this topic, I actually discuss how estimates of the number of advanced technological civilizations that would be extant at this time might vary as a result of this additional ecosystem. It doesn't require additional factors in the Drake equation. The Drake equation is perfectly good for this, but some of the individual variables in that multiplicative product go up and some go down, and it looks like that the net result is that it drives down the number of expected civilizations that we could communicate with.
Oh, Kelly, you had a question too? I have a couple after you.
Again, for Gina, the bubbles of remnant magnetism were discovered accidentally. And I guess my question is, could or should Mars Odyssey have detected its magnetometer, one of the few spacecraft that carried a magnetometer to Mars? Should or could it have detected these open field lines, these reconnection events at that time? And the other part of that question is, does this reconnection mechanism mean that these bubbles are somewhat weaker, and therefore, people have speculated that this would be a place for life maybe to cling on to existence because it's partly shielded. I guess the field strengths are what they are, right?
I was waiting for this question. Sure, so I think you mean MGS, right? Mars Global Surveyor, with its magnetometer, discovered these crustal remnant fields. So the thing is, with MGS, it went into a mapping orbit where it was surveying 2 a.m. and 2 p.m. local time, which means that it was just constantly looking at the same area of the tail. And so the unique thing about Maven is with our orbit processing, we can make nice maps of what's going on. So scientists have speculated that reconnection was going on at Mars, and we've had observations of that, but just to what extent it's actually altering the magnetosphere is what we're now able to figure out. And the results that I was showing you was just from our magnetometer itself, but we're able to use our electron and ion measurements to create these nice maps in the tail to see how the whole story comes together. So that's why we're doing something with Maven that MGS just wasn't able to do with their orbit. But they did have the instrumentation to measure that. As far as, protecting from radiation where the crustal fields are for astronauts and whatnot, it does protect underneath the surface. So if you're near the strong areas of the crustal magnetic fields, that does protect the radiation underneath. But the interesting thing is when reconnection happens and it opens these fields, it then creates a channel for the energized particles to come down towards the surface. So you sort of need to be careful with where you would use the crustal fields for shielding. And there are regions that are much more stronger than others. And we knew that this could be a threat too, because not only if reconnection wasn't occurring, there still are magnetic cusps. So there's funnels as to where these particles can channel through. So this expands those cusps. It makes them bigger, essentially.
Rick?
Yeah, this is Rick Feinberg again, AAS. A couple more questions for Alan. First question is, we've known about, we've had suspicions of an increasingly large number of these water ocean worlds in our own solar system now, going back quite some time. And I'm just wondering if you're the first to have looked at Fermi's paradox from this perspective. It surprises me in a sense that the question hasn't been asked before, because in retrospect it seems like such an obvious question to ask. So I'm curious if you've been able to determine whether other people have considered this issue.
I have
I'll
not
ask that
been
first and then wait. Go ahead.
All right. So when I had this realization, I immediately did a literature search and couldn't find anything on the topic. And I was surprised for just the same reason that you just explained, that this had been around, the ocean worlds concept, for quite a while, and we've been seeing that the existence of ocean worlds was becoming not only part of the norm in the paradigm, but the number of potential ocean worlds in our solar system was literally geometrically exploding. There may be dozens. And I was surprised to find nothing in the literature, so I called a number of colleagues who are astrobiologists, and none of them could remember papers on that topic or even that topic being discussed. It may have been, but none of them could remember it, and several of them encouraged me to write a paper, and so I did.
So my second question is, now that you've got this paper written, as this idea percolates through the astrobiology community, people are going to start to ask, well, is there some way we could tell as we begin to explore these worlds more closely, for example, the Europa mission or something like that, what kind of measurement could we make that might distinguish whether there might be life under the ocean, under the crust, versus no life under the crust? Not necessarily even intelligent, but although that would be, of course, the most exciting.
Right. Well, I think that the NASA Ocean Worlds program has answering that question as specifically one of its goals. And so over a sequence of missions to a variety of ocean worlds would eventually go from missions like Europa Clipper, which will study the characteristics of Europa's internal ocean, to actually getting down on the surface and then into the subsurface and actually visiting those abodes. in a search for life.
All right, I have one question for Alan. So what are the dangers for ocean world lives? You mentioned dangers for life on surfaces.
Yeah, I've given a little bit of thought to that, and I'm not sure that my imagination is good enough to really enumerate it. Maybe it's quite dangerous because of the interface between the planetary interior boundary below the ocean world and the ocean world itself, and there may be events like cave-ins from the roof or volcanic events that could inject both undesirable thermal characteristics into the ocean or poisonous effluents. We really are at the very beginning of understanding the characteristics of ocean worlds, and probably when we do understand them, we'll see that it may not be quite the panacea that we would think it is today. But I think that's part of the excitement, is we have this Ocean Worlds program now, and an opportunity over the next several decades to really explore a very local, not far away by parsecs or kiloparsecs, but a very local, accessible whole suite of environments that may be very similar to one another or may be very different. And I'm sure that the theory will come along with the observations. So fasten your seatbelt. The exploration of ocean worlds is beginning.
Kelly.
Hi, this is for Casey. Getting back to your comment about Morbi and forming Uranus and Neptune. You mentioned that whichever system, these systems are of order only 10 million years old.
4796, the one we looked at in detail, is the youngest one. That's 10 million.
Okay.
Then there's 30 and there's a 300.
If these solar systems, these forming solar systems follow the suit of ours, then those shepherding planets are going to migrate. And I'm wondering if you've thought about whether this is a very transient situation or something that's likely to be more permanent in these systems.
Thank you. That actually gives me a chance to explain for a minute or two. These planets are very late compared to, we're now thinking that Jupiter formed in the first million years. And our planets all the giant planets formed very early. They had to form, in order to get their giant, thick, gaseous atmospheres, they had to form the solid cores that we're seeing forming here, and then pick up the gas from the primordial disk that was around the sun. All stars start with that primordial disk. These systems, the primordial disk is gone. So one of the questions here is, why did they take so long? On the other hand, if you look through the Kepler studies and you look at the exoplanet, the zoo that is now out there, we have planets, we have styrofoam planets, we have water, we have planets that look like they're covered in very deep oceans. We have planets that are as dense as Mercury or Earth. It's very possible. We have yet to find a solar system that matches our own, despite the fact that when you and I were kids, it made plenty of sense to have all the rocky planets right near the star, and then right at the ice line is where you had the biggest planet, and then you kind of went smaller and smaller as you got to the edge of the disk. We have yet to find that in the zoo of planetary systems. So the naive ideas that everything happened just like it happened here don't seem to work. So what I would argue, what I think we're seeing here is possibly the formation of the super-Earths and these mini Neptunes, and sometimes they form later than what we expect. So, and you asked before about the cores. The cores, what we're seeing here is a stage. These have been picked out because we see these really nice narrow rings. The stage after this is when the cores start merging again, and then all heck breaks loose, and that ring breaks up. And it spreads out temporarily all over the system. That may be harder to see because it's much more diffuse.
All right. Lots of things to ponder about. So we'll end the press conference with that. And this was the last press conference for this DPS, but we'll have more next DPS. And all the press material will be available on the meeting website under press information in the press kit. Also, feel free to stalk the press presenters for any other questions. Thank you, everyone.